Cool. So now we're on the last question for the exam prep for probability and Bayes nets. So for part A, we have A, B, and C being random variables with binary domains. That basically means that A, B, and C can either be true or false each. And so how many entries are in the following probability tables, and what is the sum of the values in each table? And then we can write a question mark if we aren't given enough information. So starting with this first one, the probability of A, and B given C. Because A, B, and C are all changing, they can all either be true or false each. There are 2 times 2 times 2 rows in this table with a size of 8. Basically, A can either be true or false, B can either be true or false, and C can either be true or false, and we need all those 8 combinations. Now, as for the sum, this is a little bit tricky, but it turns out because A and B are on this left side of the conditional probability sign, because of that, we're going through each and every value of A and B. And because A, the probability of A, all the values of, or let me re-explain it as, if you go through all the values of A and then sum up all those probabilities of what A could be, that should sum up to 1. And the same thing goes for B. If you sum up all the different probabilities for B, that becomes 1 as well. So because A and B are both on the left-hand side, the sum is actually 2. We're summing over all the possible values of A and B, and because A and B can both each sum up to 1 with their probabilities, when you sum both of them together, that becomes a sum of 2 instead. Now, for the probability of A given plus B and plus C, B and C are now fixed values, so only A is the variable that's changing as either true or false. So therefore, we have a size of 2. Either A is true, in which that's one row, or A is false, in which that's another row. And in terms of sum, because A is the only value on the left-hand side, and it's a changing variable value, the sum is going to be equal to just a 1. We're summing up all the values of A in this case, and so the value is 1. The sum is 1. Now, for the probability of plus A given a variable B, the size is actually going to be 2, again, because B is the only variable that's changing in this factor, in this probability. A is fixed as plus A. Now, as for the sum, we actually do not know. The reason for that is because we do not know what the probability of plus A is. So we don't know what all of these we don't know what all of these, the probability of plus A given B are going to sum up to if we don't know what the probability of plus A itself is. So therefore, it's a question mark. Now, for part B, we want to either select true or false if these equalities are true or false, basically. So for this first one, the probability of A and B is equal to the probability of A given B times the probability of A. So this is actually false. It's almost true. In reality, the probability of A and B can actually be written as the probability of A given B, so that's right, but then times the probability of B instead of A. This is basically an application of the chain rule. The probability of A and B you can actually decompose as the probability of A given B, but then you want the probability of B back in here to reinforce this conditional probability. So this is false. Now for part 2, the probability of A given B times the probability of C given B is equal to the probability of A and C given B. Now, this would be true if A and C are conditionally independent given B. I'll just say conditionally independent given B. In fact, if two variables are conditionally independent given a third variable, this is actually one of the rules they follow. However, we are not assuming anything about these variables, so just as is, we cannot assume that this is always true. Therefore, this is false. Cool. So, as for the third one, the probability of B and C, the joint probability of B and C, is equal to the sum of the probability of B and C given A summed over all values of A. This is almost true. Now, this is the idea of sort of eliminating a variable to get another joint distribution. But instead of that sum right there, we can go through all values of A, some other irrelevant variable, but we want to sum over all the values of the probability of A and B and C instead of the probability of B and C given A. So this is true, this new sum, but this sum, this original one, is not. Finally, we have the probability of A, B, C, and D is equal to this product right here. The probability of C times the probability of D given C times the probability of A given C and D times the probability of B given A, C, and D. Now, this is actually true. This is an idea of the chain rule in action. You have, let's see, starting off, we have the probability of B given all of these values, but then all these values, A, C, and D, are all over here somewhere. We have the probability of A, but then we have given all these values, D and C, but then the probability of C and the probability of D are over here. And then finally, we have the probability of D given some other value C. But then we have the probability of C reinforced. So it's kind of like those Russian collecting nesting dolls. It's like you have a doll in a doll in a doll in a doll. And so when you have a bunch of these layers, you can kind of decompose these layers in that case. So this is actually true. So we have, again, the probability of B given some other variables, but all these variables are also enforced over here. So it's this almost recursive idea involved with this subpart. So for this final question, we're looking at the space complexity of base nets. So we're considering a joint distribution over n variables, and we let k be the domain size for each of these variables. So k is basically how many possible values can each variable take. And we let d be the maximum in degree of any node in a base net. So an in degree is basically, how many arrows point into that variable. So we want the space complexity for the first part of storing the entire joint distribution. We want to give the answer in the form of a big O notation. Cool, well, because there are n variables, and k is the domain size for each one of these variables, we can just say the space complexity is big O of k to the power of n. Because for each variable, each of the n variables, there are k different values that each variable can have, and therefore, for a joint distribution, the probability of, let's say, x1, x2, x3, all the way to xn, because each one of these n variables can store k different values, that's k times k times k times k all the way to times k n times to get all the different possible values that this joint distribution can have. So O of k to the n is the answer. Now, we want to draw an example of a Bayes net over 4 binary variables such that it takes less space to store the Bayes net itself than to store the joint distribution. So it turns out one of the ways we can do this is by making this Bayes net right here. Arrows like this. So if we have these 4 variables, these 4 binary variables, and make the Bayes net like this, how much space does it take to store the Bayes net itself? Well, for this factor right here, this variable, there are only 2 values. It's either true or false. Now, for this variable right here, it is dependent on this variable because it's pointing to that variable. So there are 2 times 2 different values for this factor. Either this is true and this is true and this is false and this is true, or this is false and this is false. So there are 4 values there. Same thing goes with this variable. Since this one variable is pointing to that variable, there are 2 times 2 different values for this factor. And then finally, for this variable right here, there are 2 times 2 different values for this factor because this arrow is pointing to that node, or that, I guess, variable. So if we add up all of these factor entries, we get 2 plus 4 plus 4 plus 4, which is equal to 14. Now, to store the entire joint distribution, if we say this is x1, x2, x3, and x4, the joint distribution probability of x1, x2, x3, and x4 would be size 2 times 2 times 2 times 2, or 16. Because, remember, every variable is either true or false. They're 4 binary variables. So to store the entire joint distribution, you have to look at all 16 different possibilities that these 4 variables can be. So therefore, it takes less space, in this case 14 rows, to store the Bayes net than to store the entire joint distribution, which is 16. And for this third example, we want an example of a Bayes net over 4 binary variables such that it takes more space to store the Bayes net than to store the joint distribution. And after playing around with it a little bit, you can come up with this idea where you have 3 of the variables pointing to one of them. Now, still, the joint distribution is the exact same. It's still 16. However, to store the Bayes net, we have 2 values here for this variable, either true or false, 2 values over here for this variable, either true or false, and then 2 values over here for this variable, either true or false. However, for this 4th variable, you have 2 times 2 times 2 times 2 values to store for this factor, because this variable has 3 arrows going towards it, so 3 variables are have a possible correlation to this variable right here. So therefore, if you were to try to make the factor for this variable, you need to take into account these other 3 variables and their, I guess, sizes. So therefore, that's 16. So to store this Bayes net, the space it takes is 16 plus 2 plus 2 plus 2, which is, I believe, 22. And since 22 is bigger than 16, which is the storage which is the amount to store the joint distribution, this is the Bayes net, in which it will take more space to store the Bayes net than to store the joint distribution.